But first, before we do that, I want to do kind of a quick look at a different type of infinity before we have that review problem. So what we just looked at was LF null. And LF null is the cardinality of natural numbers. It also is the cardinality, so I could set up a one-to-one correspondence, basically is what this is saying, of the natural numbers with the whole numbers. I also could do it with the integers, and I could do it with the rational numbers. The whole numbers aren't hard to do. The integers and rationals can get a little nastier, so you probably don't want to see that one. We did sets like this, sets where we're skip counting. That's what we did, all of these. We were skip counting on that B, C, and D, so we did that. And they are all countably infinite. Now, basically everything in the world, all these infinity things, ones with the dot, 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 or these other names like this, they are all had that cardinality LF null. There are only two cases where it's not LF null. There are two special cases, the real numbers and the irrational numbers. Remember, we looked at those in 6.4. They are wonky. Remember the irrational numbers? We said they are not rational. They do all this sort of crazy things. And then the irrational numbers are part of the real numbers. So these two cases are where we're going to have not LF null. So we have a different name for them. We call them the continuum. And you'll see me just write a C for continuum. It's actually usually written as a slanty C for continuum. And we call these uncountably infinite. And that just means there's not a pattern to them. We looked at, when we did irrational numbers, there's no easy way to write them all out. There's no pattern to them. So they are uncountably infinite. And so we use that C for continuum. And there's a crazy cool proof for that. I would love to show it to you if we have time in class. Probably not something for the video on this, though. You're just going to take my word for it. Sorry about that. But let's look at this set here. So this kind of, we're going to be using the infinite sets, the LF null and the continuum here, to look at these guys. And for these, we're going to have numbers all over, answers all over the place. We want to know the cardinal numbers for each set. Well, looking at that, this set A and set D, they are not infinite. They stop. Set A has 4 letters in it. Set D is the set of months. I know April's not in there. Remember, that ellipse is in the middle because I'm lazy and don't want to run them all out. There are 12 months in the year. Those two are the ones that have actual number answers. The rest of these guys, oops, O and F, I'm sorry, F as well, has a set number. And that's because they all have something at the end, right? There's a final answer to it. So this one also is going to have a number answer. I'm going to use what we did in the Gauss sum back in chapter 1 to find the number of items in the set. So a little bit of review. Oops. From our earlier. We use that to find the number of items in the set. You can also just write it out if you wanted to. There, 43 is the largest number, 13 is the smallest number. Where it looks like we're counting by 2s on this one. We're skipping a number each time, and then +1. And we got to add that +1 at the very, very end. If I type that in my calculator, there are 21 items. You also could list it out on count on your hands, but I thought I'd do a throwback to that Gauss sum from back in the other chapter. So those 3 have a number answer because they have something at the very end. These other guys are all some type of infinity. There are only 2 special cases that are the continuum. It is the real numbers and the irrational numbers. So the real numbers are the continuum. Everything else is LF null. So I get my LF null there. All right, so here's that other example I was telling you about of setting up the one-to-one correspondence. So if you haven't tried any, you really need to pause the video and try this one. and then come back to it. So I would like everybody to give it a shot, hit pause, try to set up the correspondence. It should work. You gotta do the weird finding that formula at the end. All right, coming back from the pause, our natural numbers, I'm gonna pair up with our set that we were given. And I should have mentioned this before, so I apologize for not. I should have. This is actually going to use subtraction. So you can have adding or subtracting, either case. And honestly, adding is a lot easier to come up with. So my math lab, a lot of them will be adding, but you can do subtraction. They're a little bit harder to come up with, so we don't have quite as many examples of those. Just to remind yourself, you need that part, you need the ellipse, and then you also are going to need this part at the end. So 3 parts to get full credit. So we want 1 to turn into 8. Right now, I know we are counting by tens. So I'm going to start with 10 in. But again, when I plug in 1, I want the answer to be 8. So if I plug in 1, I get an answer of 10. But it needs to be 8. So to get 10 to turn into 8, I subtract 2 to get that final answer there.